Okay, hello everybody and welcome to Metcom's Functional Performance webinar. My name is Omar Arafat, Project Metallurgist at Metcom, and I will be the moderator for today's presentation. We're very excited to be broadcasting this session today, which will be the first of what we plan to be an ongoing series of webinars. These functional performance webinar presentations will be focused on providing metallurgists and those working with grinding circuits with some practical and useful tools that can be applied at the plants. We've gotten a lot of positive feedback from our grinding bulletins, and we see these as this platform as being an even more effective way of reaching the people in the industry and giving them some useful tools that they can apply at their jobs. So today's webinar is titled Grinding Circuit CSE, Energy Applied Where It Is Needed. And CSE stands for Classification System Efficiency, which will be the focus of Rob's talk today. So before we get started, I'd just like to quickly familiarize you with this webinar platform and the format for this session. We anticipate this session lasting for around 45 minutes, which will include a 15-minute Q&A session at the end of Rob's presentation. In the event that we run out of time or can't get to all the questions, we'll make sure to reply directly to you by email. So on the right-hand side of your screen, you should see the chat box. This can be minimized or maximized just by clicking on the little red tab. Please feel free to use this feature to type in questions or comments throughout the presentation, and we'll definitely address them in the Q&A session immediately following. You might just want to test this out, just giving us a quick hello. I think some of you have already done this. And please let me know if you experience any audio or video issues on your end. Great. So without any further preamble, let me begin by introducing our presenter today, Robert McIvor. Rob is founder and chief metallurgist of Metcom. He's a graduate of McGill University and has compiled 40 years of experience related to the design and operation and optimization of industrial grinding circuits. He has worked in process equipment application engineering for manufacturers of grinding mills, slurry pumps, and hydrocyclones. He has also spent several years at the Operating Plant Process Improvement Department at Cleveland Cliffs. He is the discoverer of grinding circuit classification system efficiency, which is the topic of today's webinar, as well as the functional performance equation for milling circuits. He oversaw the development of a complete systematic program for measuring and improving the process performance of plant grinding operations and its delivery to industry practitioners through Metcom's comprehensive web-based training program. And I will now turn over this presentation to Rob.
Thank you, Omar. And once again, everyone, thank you for joining us for the first of our series in webinars on functional performance of grinding circuits. Today, I will introduce you to Grinding Circuit Classification System Efficiency, or CSE for short. This is one of the most powerful tools in our entire tool set. You will see it is quite simple and very practical. We can readily measure it, and then we can manipulate it to increase grinding circuit efficiency. We hope that after this webinar, you will be motivated to put it to use to increase grinding circuit efficiency, as many others are now doing. So let's get started with what is CSE. So on this slide, you see the typical grinding circuit consisting of the ball mill, pump, and hydrocyclones. So let's say that this circuit is grinding to a P80 size of 106 microns. I just underline that in the upper right-hand corner, and I think the whiteboard is coming through in a few seconds. Now, all the grinding is being performed inside the mill, and 100% of the power driving the mill is being absorbed by the mill contents, the balls interacting with the solids in the slurry. But how much of this total power is generating new minus 106 micron size material? That depends on the percentage of the solids in the mill that is coarser than 106 microns. Any energy expended on minus 106 microns is wasted. So a great way to express the efficiency of the total power usage of the mill is to ask what percentage of the mill power is being expended on coarse material, that is, material larger than the P80 size. We can call the percentage of plus P80 size material in the mill, which is the same as the percentage of the mill power being used to grind the plus P80 size. We call this the circuit classification system efficiency, or CSE. We can also call this the coarse solids energy, which is another way to picture what we mean by CSE. So the question is, what is the percentage of plus 106 micron material in the mill? How can we measure that? Well, the question really is, what is the size distribution of the solids in the ball mill? Now, this has actually been measured on a few occasions. For example, in the pilot plant work carried out by Professor Davis at the University of Minnesota, as shown in the next slide. So what is plotted here are the three size distributions. The blue line is the size distribution of the material entering the ball mill. The red line is the size distribution of the material discharging the ball mill. And the intermediate line is the size distribution of the actual mill contents. This was a ball mill circuit set up in closed circuit, grinding to a P80 of, say, 150 microns. And with the classifier product being, say, 150 microns. And Professor Davis sampled the circuit and then crash stopped it, dumped the mill contents, and then actually did a size analysis of the entire mill contents. So from this, you can see, if you compare the actual mill contents, and I'm just overlaying it here with the whiteboard, to the mill feed and discharge, you can see that the mill contents is pretty well represented by the average of what's going in and out of the mill. So if we take a particular size, if we have the size analysis of the mill feed and the size analysis of the mill product, we can estimate the amount of that material inside the mill. So this allows us to calculate the percentage of plus P80 size material in the mill. And let's do an example of that on this next slide. So we're taking a sample of the ball mill feed or cyclone underflow and doing a size analysis. And then we take a product of the ball mill discharge and do a size analysis. Then to calculate the percent CSE, the percentage of the mill energy being used on coarse material, we take the average of the coarse percentage in each of those two. So take the percentage of coarse in the ball mill feed. In this example, it's 77% plus 106 micron. Take a sample of the mill discharge, 65% plus 106 microns. And we take the average and come up with the overall estimate of 71%. This is the percentage of material in the mill coarser than the P80. And it tells us the portion of the total mill power consumption which we are effectively using. So immediately you can see one of the great strengths of this performance parameter, CSE. It's extremely easy or simple to calculate. All we need to do is to sample the mill feed and the mill discharge, and then by taking the those size distributions of those samples, we can then calculate the percentage of coarse material in the mill. So these data then tell us exactly how well we are making use of our ball mill power. That is, the percentage of the power grinding plus P80 size material. So we can measure our CSE both simply and accurately. So the question is then, do I have any influence over what my CSE may be? And the answer to that question is a definite yes. The first step is to recognize that the CSE for any circuit depends on the setup of the pumps and the cyclones. The mill grinds whatever is inside it. That is, it is the function of the mill to do the grinding. It is the function of the pump and cyclones to ensure that the mill contains as much coarse material as possible. That is, to maximize CSE. Analysis and optimization of these two distinct functions, A, the ball mill, and B, the classification equipment, is what we call functional performance of ball milling circuits. So, how would we go about maximizing CSE? And that's a question of what circuit design and operating factors affect CSE. From this slide, we can see that the amount of fines or minus size material in the mill depends on what's going in the hydrocyclone underflow. So clearly we want that to be minimized. But also the amount in the discharge depends on how long the material is in the mill. If the residence time is very long, we'll have a large buildup of fines, and the mill will contain a lot of product size material. If it's very short, that is a high throughput or high circulating load ratio, then we have a minimum buildup of fines. Now, Professor Davis also ran a pilot plant in which he operated his circuit first in open circuit, that is with a circulating load of 0, no classification equipment. And then he closed circuited his mill with a classifier and ran it at increasing circulating load ratios. So starting in open circuit, the production rate of new minus 150 mesh or minus 106 micron material was 100 tons an hour on a relative basis. So in open circuit, his mill was able to produce 100 tons an hour of new minus 106 micron material. Then by closed circuiting the mill, the circulating load of, say, 200%, the capacity of the circuit increased all the way up to 220 tons an hour. So by closed circuiting and operating with a circulating load of 200%, that is, the mass flow through the mill was 2 times the tonnage of the circuit, the productivity of the circuit more than doubled. And so on, pushing the circulating load up to 400, 500, 600%. Ultimately, the capacity of the circuit was 2.6 to 2.7 times greater than the circuit in open circuit. So this was all done with the same ball mill power and the same final product sizing. So we all know that we operate ball mills in closed circuit with cyclones and generally with high circulating load ratios. And that is because they then give us 2 to 3 times the production rate with the same amount of power. That is 2 to 3 times the circuit efficiency compared to open circuit. But why is that? Well, imagine a ball mill running an open circuit without any external classification equipment. A lengthy residence time is needed to grind all the way to the product size in one pass. The mill discharge itself would be 80% passing the P80 size. So at least near the discharge end of the mill, only 20% of the power is going to the grinding of coarse plus P80 size material, and 80% is being wasted. Depending on the size distribution of the mill feed and the back mixing conditions, an extremely large portion of the mill power is being wasted. Now contrast this with a circuit with a very high circulating load. That is a very short mill residence time. As soon as the fines are generated, or very quickly, they are moved to the classifier and removed from the circuit. Many studies in plants, pilot plants, and computer simulations all lead to the same conclusion. The net steady state condition that maximizes the proportion of coarse material in the mill, that is, which maximizes CSE, is that achieved with minimum residence time. And that corresponds to the maximum circulating load ratio. You'll note that the Davis curve levels off towards the right, is starting to flatten out, but in fact continues to increase ever slowly as you increase the circulating load even up to 700-800% and beyond. we've measured the classification system efficiency in a plant that was operating with a circulating load of near 1,000%, and it was near 90%, the highest we've ever measured. So the only limitation on increasing circuit productivity by increasing the circulating load are practical things like the flow rate gets so high that you're washing the balls out of the mill, or pumping power, or maintenance of the pumps and cyclones gets to be so high because of the high flow rates. So what is actually happening then as we go from low circulating loads to high circulating loads? And we can see that in the next slide. This slide shows two circuits, both with the same feed size and product sizing, again a P80 of near 106 microns. And the shaded areas show the size distributions in and out of these mills. One with a low circulating load, around 150%, and then the other with a very high circulating load, about 600%. The shaded area with the circuit with the low circulating load shows the mill contents. The bottom line is the mill feed, the top the mill product, and the shaded area in between represent what's inside the ball mill. If you compare the, look at the amount finer than the P80. It's roughly, 25% of the material is finer than the P80 to the left of the curve, and 75% is to the right of the curve. So in this case, the classification system efficiency is close to 75%. Compared to the bottom set of curves and the contents of the mill with a high circulating load, about 600%, the overall size distributions entering and discharging the mill are about 85% coarser than the P80 and 15% finer. So we know in this case, by increasing the circulating load, we've increased the classification system efficiency from about 75% to 85%, and effectively use 85% of our mill power instead of 75%. Another example of this is given on the next slide. This was a computer modeling study, starting with data from the Craigmont milling operation. They had a very low circulating load, 160%. The circuit production rate was 203 tons an hour. And by setting up the circuit on the computer and manipulating the classification equipment, we were able to increase the circulating load to 500%. In doing so, we were able to increase the tonnage up to 262 tons an hour. That's an increase in throughput of 29%. By looking at the size distributions going in and out of the mill, we're also able to see that at the low circulating load ratio, the mill contained 55% material coarser than the P80. At the high circulating load, it contained 71% coarser than the P80, an increase of 29%. So the increase in circuit production rate came about specifically as a result of increasing the usage, the effective usage of the available energy, and that was being done by manipulation of the pumps and the cyclones. So the first very important factor in maximizing CSE is to have a high circulating load ratio. Okay. The second factor that we found to be extremely important in maximizing the classification system efficiency is the water balance at the cyclones. Now this next curve shows a typical size-by-size recovery performance of hydrocyclones in a grinding circuit. The dark blue points are the actual size-by-size recoveries to underflow, and the pink points and line are the reduced recovery to underflow, which you obtain by subtracting the fines in the bypass. So what this graph shows is that a hydrocyclone is far from being a perfect classifier. If we had perfect classification, say at the cut size, the D50C cut size here of about 150 microns, we would have a vertical line running from that point up to 100% recovery, excuse me, and every particle coarser than that would be recovered to underflow at 100%. Below that, again, any particle finer than that would be recovered at 0% to underflow. So from the dark blue points, you can see that the actual separation performance of a hydrocyclone is far from perfect. The greatest cause of the imperfection is the bypass fraction. You can see that these fine points, the recovery of the finer size fraction, levels off in this case at around 45%. This is the bypass of fines to the cyclone underflow from the feed, and is also equal to or very close to the bypass of water from the cyclone feed to the underflow. So this bypass fraction of fines is associated with the recovery of water from the cyclone feed to the underflow, in this case about 45%. So those fines being carried into the ball mill, we don't want them there. So one way we can minimize those fines being carried back to the ball mill is to reduce the bypass fraction. To do that, we have to change the water balance at the cyclone. Now, the mass flow of water to the underflow, let's say it's fixed because the percent solids there is fixed and the circulating load is fixed. If we can increase the amount of water in the cyclone feed and have it report to the overflow, then the fraction of the water which reports to the underflow will be reduced. And that's what we see in this next slide. By changing the water balance at the cyclone, which involves making adjustments to the cyclone dimensions and the pumps and so on, we reduce the overall bypass from 45% down to about 40%. And this in turn reduces the fines going back into the mill and therefore increases CSE. Now, this can be a very important factor depending on the water balance, as shown in the next slide. This table summarizes a computerized grinding circuit study of increasing water addition to the cyclone feed in the grinding circuit. So on the left-hand column, you've got the cyclone overflow percent solids. The second case, 42%, was the operating data used as the basis for the simulations. But the actual operating case at the plant, Barrick Tuluwaka, was 50% solids in the cyclone overflow. They needed such a high density because they were feeding the product to a CIL circuit. So the question was, by increasing the water usage of the cyclones, how much would this improve the performance of the grinding circuit? So we conducted this simulation study of adding more and more water to the cyclone feed, in each case the water eventually reporting to cyclone overflow, so reducing the cyclone overflow percent solids all the way down to 10% in 10% increments. Each case involved adjustments to the pumps in the cyclones, and then running the simulation to see how much grinding mill power was then needed to achieve the same grind of 80% passing 106 micron. If you look at the columns, the recovery of water, and B, the bypass, you can see they pretty much follow one another. Initially, the bypass was close to 47 to 49%. And as the water addition to the cyclone feed was increased and increased, the bypass was reduced all the way down to 10%. And running the simulations, we saw that the mill kilowatts needed was reduced from 580 all the way down to 430. And the classification system efficiency associated with each run is shown, starting with the existing circuit in the plant of 64% and increasing all the way up to 86% with increased water addition to the cyclone. That's an overall increase in circuit efficiency of over 30%. Now, Barrick actually implemented this idea by moving a thickener over to where the grinding circuit was located and putting a lot more water into the cyclone feed. And they obtained a substantial increase in throughput, ground much finer, and increased their gold recovery significantly. So first, this table tells us there is a very large increase in CSC available by working with the water balance at the cyclone, that is, by reducing the bypass fraction. Another important thing we can note from this is the excuse me, the large reduction in overgrinding. In the base case, 64% of our energy is being used effectively. 36% is being wasted. So we're actually wasting 36% of 580 kilowatts, which is about 210 kilowatts. In the optimized case of 10% solids in the cyclone overflow, we're now only wasting 14% of our energy. 14% of the required 430 kilowatts is 60 kilowatts. So what we've done by capturing and using the energy more effectively, we've also reduced grinding substantially from 210 kilowatts down to 60 kilowatts. So what we're doing when we're increasing CSE is recapturing energy that is being wasted on overgrinding. And this can be extremely important in processes like flotation that are sensitive to overgrinding and loss of extremely fine particles because of overgrinding. You'll note that the actual energy applied to create the product size of 80% passing 106 micron is the same in every case, whether you take 64% of 580 kilowatts, 71% of 523 kilowatts, or 86% of 430 kilowatts. In all cases, we're still using the same amount of energy to grind, about 370 kilowatts. We're just making better use of the available mill energy. Okay, there's a third very important use for this table, which you'll be able to refer to. And that is, it tells you your achievable CSE for your grinding circuit, depending on whatever limitation you have for cyclone overflow. For example, if you have 30% solids in your cyclone overflow, and that's the requirement for flotation, you should be able to achieve at least 78% CSE. So when you go out and measure your CSE, unless you're close to CSE, this gives you a good measure of your potential room for improvement. These simulations were carried out all with the same circulating load, around 350%, and all using standard, basic design, old style cyclones. So the improvement in CSE, the value of the CSE achieved as shown in this table is actually conservative. And you should be able to achieve these CSE values depending on the limitation that you have for your cyclone overflow. Now, you should be considering what is the percent solids requirement of the feed to my downstream process. If you're producing cyclone overflow at 35% solids and adding water to dilute the feed to your downstream process to say 30%, by moving that water back into the feed to the cyclones, then there's absolutely significant potential for improvement. Okay, so we've seen that the two really important factors for maximizing CSE are first, circulating load ratio, and then secondly, the water balance. Well, the third most important factor is the separation sharpness of the cyclone itself. And on this previous slide, we see this actual recoveries, again, the dark dots, and the reduced recoveries to underflow. And this is a high efficiency cyclone, one of the newer designs created by the cyclone manufacturers over recent decades with the aid of CFD and so on. And these cyclones give a sharper overall separation performance than older design cyclones. And we can characterize the sharpness of separation by the slope of this curve, which I've just imposed in. And then if we compare it to an old style cyclone, we can see that we've got significantly improved separation sharpness with newer design cyclones. Now this contributes, at least in a small way, to improved CSE, a small positive way to CSE. So we want to take advantage of that. But another advantage of the new modern cyclones is they have a lower pressure drop at the same flow rate. So with the same pump and cyclones, we can increase the flow rate through the cyclones. That is, we could increase the circulating load ratio, or we could improve the water balance. So we want to take advantage of that. Another thing that you'll note about the difference in the performance of these standard versus newer cyclones is the very coarse particle range. Up here, you'll see that we're losing some very coarse particles to the cyclone overflow where we definitely don't want them. Whereas with the newer, higher efficiency, high performance cyclones, it's actually collecting all those particles, 100% of them, to underflow. So this is the third factor in obtaining high CSE, and that is the use of well-designed, modern, high-efficiency cyclones. So to summarize, in order to maximize the CSE in our grinding circuit, to make maximum use of the available power, we want to design the setup of the pumps and cyclones, first of all, to provide a high circulating load ratio. And that's what we mean by high is normally in the range of 350 to 400%. Secondly, we want to maximize cyclone water usage. That means minimizing the bypass of water and fines to the underflow. And thirdly, we want to provide ourselves with the use of modern design cyclones, get better overall sharpness of separation, and be able to handle higher circulating loads and improved water balance with the same pumping equipment. So what are the next steps? Well, the first thing would be to go out and compare the grinding circuits that you're working with, to compare their CSE to the reference database, which is shown in slide 10. So by taking samples of feed and discharge and knowing the limitation of the cyclone overflow percent solids, compare that to the P80, and you can see where you should be or what you should be able to achieve in terms of CSE, and include the potential for dilution, increased dilution of cyclone overflow. You can also review the general methodology for adjusting the pumps and cyclones, and a large number of case studies that have been published in Mining Engineering magazine. And these publications are available on our website. And finally, you can use Metcom web-based training to add your circuit to the list of increased grinding circuit CSE success stories. Thank you for your attention, and I'd be glad to try to answer any questions you might have.
Okay, great. Thanks, Rob. You can use the chat box to ask any questions, and we'll be happy to answer them. We'll just give you a second to type in your questions.
Excuse me.
Okay, we have a question in the private, sent privately. Um, how can an increase in the CSE metric be exploited, Rob?
Um, if you can increase your grinding circuit efficiency, there's three things that you can do. The first thing would be to say, okay, let's run the same ore, the same tonnage, the same grind, and let's reduce our energy consumption. And you would do that by reducing your ball charge level. And then you would save money on grinding energy and grinding balls, and those are a huge cost in your plant. So that's always an option if you increase grinding circuit efficiency, whether it's by increasing CSE or any other method. A second thing that you could do is to grind finer. If you're looking for a finer grind in order to increase downstream recovery, that gives you capability to do that. Now, if you're running at the grind that you want, and you can increase your tonnage as an alternative to grinding finer, as long as you're not constrained by tons of ore available from the mine or other downstream processes, tailings handling, and so on and so forth. So those are the three options that you always have when you find a way to increase efficiency. You can reduce costs, you can grind finer, or you can increase tonnage, or some combination of those.
Great, thanks. Brewire has a question. He's asking about what about segregation of particle size distribution in the mill?
Yeah, there's definitely a buildup of the coarser size particles in the mill. We've seen that. However, when we're dealing with the P80 size, it is generally very well represented by the average of the mill feed and the mill discharge. That's because it's generally a finer particle size, often 75 microns, 100 microns, sometimes 200 microns, but it's generally associated with a finer particle size, which is associated with pretty much a straight flow through the mill, and no significant buildup of that size because of any gravity size effects. But that's a very good point. When you're talking about the coarser size particles, 10 millimeters, let's say, there can very, very well be a buildup of those sizes in the mill, such that the average content of that size is not represented by what's in the feed and the discharge. So yeah, we appreciate that, but in generally applying this to the P80 of a ball milling circuit is not a problem.
Okay, Jan has a question. Do we have similar experience for autogenous and pebble mill grinding circuits?
Again, a very interesting question. We believe that this principle applies to any type of milling circuit. That is, we want to expend our energy on coarse particles. That is particles coarser than the product size. So we generally are applying this to overflow ball mills because we know that we can estimate the size distribution of what's in the mill. If we have a great discharge, like we might have in a ball mill or a pebble mill, or that we have in a sag mill, then it's much more difficult to estimate what is the size distribution in the mill. But nevertheless, the principle applies that if we can estimate the size distribution of what's in the mill, we can then estimate the percentage of the mill contents and the percentage of the mill energy being expended on what we call coarse particles. In the case of a sag circuit, let's say you have a 12 millimeter screen, then the CSE for that sag mill would be the percentage of the mill contents coarser than 12 millimeters, say. So the principle applies, but in generally we're applying this to overflow ball mills, and we're using this to optimize the setup of the pumps and the cyclones in order to increase the efficiency. And of course, there are many, many, many overflow ball mills out there to work on.
Okay. So if there are no further questions, I think we'll wrap up this webinar session. We hope that you found it useful and you're able to make use of this valuable tool at the plants you're working with. We encourage you to visit our website, metcomtech.com. where you'll find the the two mining engineering magazine articles on CSE that Rob had mentioned, as well as more information on CSE, our training programs, software, and other resources. We'll be sending all of you a copy of today's slides presentation and a special offer for our CSE training program. I thank you very much for attending this session, and if you'll be at the SME conference in Minneapolis in February, please stop by the Metcom booth in the exhibit hall and say hello. Also, both Rob and myself will be at the National CMP meeting in Ottawa next month, and we hope to see some of you there as well. We'll be sending out email notices for future functional performance webinars as they come up, and we're hoping that you can attend those as well. So again, thanks for your time and attention, and I believe we'll be signing off now. Thank you.
Thanks, everyone. Bye for now.
Bye-bye.